if you substitute 1 to the second equation, then you will find out that y should be 2. So yes, this point of interceptions of these two lines is the solution of the system of equations. And so that's the first picture. We have each row for when we have just two variables, then each row represents a line, and intersection of these two lines is the solution. And the column picture. And in order, so we can also write this system of equations using slightly different notation. So first we need to write coefficients in front of x-axis. So in the first equation, in front of x is 1, and in the other one is the same. So we can write it like this. In the case of y's, we have -1 and 1. And the right-hand side has these two numbers, -1 and 3. Okay, so we can draw these three vectors. So we have 1 and -1. So in this case, axes are y and x and y. In this case, we will use E1 and E2. So E1 refers to the first component, or components of these vectors, and E2 is for second. And yes, so the first vector has these two components, 1 and 1. The second vector is -1 and 1. And I will use different color to draw this vector -1, 3. So it is 2 and 3. Okay. And if we want to solve this system of linear equations, we can interpret the solving as finding these coefficients of linear combination. So we want to find x and y such that when you multiply this vector, this first vector by x and the other one by y, then you will obtain -1 and 3. So we know that the solution is 1 and 2, so we need to multiply the first vector by 1. So the first one is 1, 1, so this is just the same, and the second vector should be multiplied by 2. So it will look like this, and then you can check if this linear combination looks fine. Okay, so yeah, this is how you can illustrate it in this column picture. So in the case of column picture, we are looking for coefficients of linear combination that will give the vector on the right. Okay, and so now we have these two illustrations, and yes, we can continue with this problem number 1. So we have also to multiply the first vector by 2 and write the resulting system of equations and draw corresponding row and column pictures. So let's do it. Okay, so I need to okay, I would like to okay. So after multiplication of okay, let's change this size. So if we multiply the first equation by 2, then we will obtain 2x minus 2y is equal to -2, and x plus y is 3. So in the case of the row picture, it won't change. Okay, it's because we just multiplied one of these equations, and if you want to draw it, then the same points are the solutions of this first equation. So the line representing it won't change, but this column picture will change. So we can write the system of equations using this the notation with column vectors. So in this case, we have these two coefficients. So now we have 2 and 1 multiplied by x. Then we have -2 and 1 multiplied by y, and -2 and 3. So that's the first vector. The second is -2 and 1, and finally -2 and 3. And of course, the solution to the system of equations won't change. So the first vector is multiplied by 1. The second vector is multiplied by 2, and addition of these two vectors should give the same result as the right-hand side vector. Okay, and yes, the next thing we have to do is to draw this row and column picture for the system obtained by subtracting the first row from the second row. Okay, so we can, but we start with this. I would start with this first version of. So I will subtract the first row from the second one, but starting from from this original system of equations. Okay, so I will try to clear. Okay. Okay. Yes, so now after subtraction of the first equation from the second one, we can write the following. So we have x, y minus y is -1, and then we subtract the first equation from the second one, so it will x minus x is 0, and y minus -y is 2y, and 3 minus -1 is 4. Okay. So now we can draw this row picture. So the first line will be the same as earlier. So we have this is the same as y is x plus 1. So it should be like this. And then the second equation is the same as y is equal to 2. So it will be a horizontal line, and we can see that we have still the same solution here. So f x is equal to 1 and y is equal to 2. And the column picture for this modified system of linear equations, then so we can also write it using this notation with vertical vectors. So in the case of x, we have these coefficients 1 and 0. Then have minus -1 and 2 multiplied by y, and -1 and 4. So the first vector has these coefficients 1 and 0, components 1 and 0, so it should be like this. Then you have -1 and 2. Finally, -1 and 4. Okay, so again, we need to multiply the first vector by 1, and the second vector should be multiplied by 2, and then if you sum these two vectors, then you will obtain -1 and 4. So still we have the same solution. So we have, although we have different vectors, but the coefficients of their linear combination is still the same. Okay, and
sir, one question.
yes.
Like, what is the interpretation of the E2 and E1? Like, is it as E2 is for the first, is for second vector, E1 is for the first vector?
No, it is, no. E1 is the axis for first components of these vectors, and E2 is for the second components of these vectors. So each vector has these two components, and yeah, E1 and E2 is just a notation for the axes that refer to these components, because we can't write X and Y like in this row illustration, but we need to use different names for these numbers. So I use E1 and E2. In this book by Gilbert Strang, these axes are not described at all. Okay, so yeah, so it is so. Yeah, but it's better to have some descriptions of axes. So I use these E1 and E2, and I just say every time I use it that E1 it refers to the first components and E2 refers to second components of these vectors.
Okay.
So let's move forward. And then, yes, so what will happen if we interchange rows? So, yes, so after interchanging row picture will remain the same, okay, because we will have the same lines. But how about this column picture? Yeah, we need to, then these components will be interchanged, and so this will be the same as changing axes. Okay, so we need to make some flipping of this picture. So yeah, I will draw it. So let me struggle with this paint angles. Okay, and then I need to do. Yes, so I will do this picture for interchanged rows using this this system as a starting point. So after interchanging of rows, the first row is 2y is equal to 4, and the second is x minus y is equal to 1, negative 1. And using this vector notation, we have two. No. Yeah. So it will be 0 and 1 multiplied by x plus 2 and minus 1 multiplied by y and 4 negative 1. So now we have vector 0, 1. So it will be something like this, then 2 minus 1. And this right-hand vector will be 4 minus 1. So we have the first 4, and the second component is minus 1. So that's it. Okay, and after multiplication of the first vector by 1, it will remain the same. And if we multiply the second vector by 2, then it will look like this. And after addition of these two vectors, so as I explained it last time, you can think of it as moving this arrow somewhere here, you will end up on this right-hand side vector 4 minus 1. Okay, so that's all about this problem number 1. So if you have any questions about these two interpretation or these two illustrations of systems of linear equations, I'd be happy to answer it. If not, I would try with this second exercise to draw planes in row picture of the following system of equations. So yeah, it will be rather hard to draw it, but I will try. So in this case, we have a free system. So let me write this whole system of linear equations. So it has all ones and zeros, which typically we don't write. So we have 1x plus 0y plus 0z is 2. Then we have 0x plus 1y plus 0z is 3. And the third one is 0x plus 0y plus 1z is 4. So now each equation has three variables, x, y, and z. Typically, we don't write these 0y or 0z, but as the whole system has these three variables, you need to think about each of these systems, about each of these equations as equations with these three variables. So we need to think about this three-dimensional space. So in this case, each equation represents a plane in three-dimensional space. So yeah, so if we want to draw it, it will be rather difficult, but so we have these three axes, x, y, z, and the first equation solutions to the first equations need to have x equal to 2, and no matter what y and z are. So we need to have x equal to 2. So yeah, I will draw these two lines. Okay. One is parallel to this y-axis, and the other one is parallel to this z-axis, and all points spanned by these two lines are the solutions to this first equation. Okay, so we can illustrate this first equation as a plane, which is parallel to a plane spanned by y and z axis, but shifted to the right, in such that it intercepts this 2 point. Okay, and yeah, the next equation is as y is equal to 3. So in this case, y is equal to 3, no matter how x and z values are. So in this case, I could draw a line that is parallel to this z-axis and a line which is parallel to x-axis. And all points spanned by these two lines are solutions to the second equation. And finally, we have this third equation. So z is equal to 4. So in this case, I can draw this line which is parallel to x and the line which is parallel to y, and then all points on this plane spanned by these lines are solutions to this third equation. Okay, so now I will try to okay, then we have, so in this case the solution to the system of equations is 2, 3, 4. So let's locate this point. So the first is 2, then is 3, and it should be somewhere here. So I will use a different color. Okay. So this is the point where these three planes have their where these three planes intercept. Okay, so that's the point. And okay, so you can imagine these three planes, and they have this common point with coordinates 2, 3, 4. In the case of this column picture, we can write this kind of equation. So the coefficients in front of x's are 1, 0, 0. Then we have 0, 1, 0 times y plus 0, 0, 1 multiplied by z is 2, 3, 4. So now we have this coordinate system with E1, E2, and E3. Yes, so the first vector has components 1, 0, 0. So I will draw it with this blue color. Then we have the second is 0, 1, 0. And the third one is 0, 0, 1. And we have this vector on the right, which is 2, 3, 4. So the first component is 2, the second is 3, and the third component is 4. So we can draw this So if we multiply this first blue vector by 2, the second by 3, and the third by 4, we will obtain this vector 2, 3, 4. Okay, so let's read this text for problem number 2. So 3 sides of a box meet at the solution 2, 3, 4. Draw vectors in the column picture. 2 times column 1 plus 3 times column 2 plus 4 times column 3 equals the side. Okay, so I think that's all about this exercise number 2. Yeah, I will check if you wrote any questions on the chat. Okay, at some point, I think, yeah, it was about 20 minutes ago, so maybe I corrected them. This some mistake. Yes, so let's move to this exercise, to this problem number 3. So if the equation in the previous problem are equations in the previous problem are multiplied by 2, 3, 4, they become, and we have this system of equations, so I can write it here. So it is 2x. So the first equation was multiplied by 2. So we have 2x plus 0y plus 0z is 4. Then we have 0x plus 3y plus 0z is 9. And 0x plus 0y plus 4z is 16. Why is the row picture the same? It's because we discussed it earlier for the case of this two-dimensional system, but each row represents a plane, and if we multiply equation of a plane by a number, that it won't change this plane. Is the solution to the new system the same as to the previous one? So as the row picture is the same, then this solution remain the same. And what is changed in the column picture? Yes, so we have these new vectors then, so we can think of it as a scaled version of this previous column picture. One, E2 and E3. Times x, 0, 3, 0 times y plus 0, 0, 4 times z should be 4, 9, 16. Yes, so the first vector will be also in this first axis, but it will be multiplied by 2. The second vector will be multiplied by 3. And the third is multiplied by 4. And we have this vector at the right side, so it is 4, 9, 16. Okay, so we have 2, 3, 4. then we have 9, so 3, 4, 5, 6, 7, 8, 9, and then we have 16, so yeah, it is outside this picture 4, 9, 16, but the solution will be the same. If so, now I will read problem number 4. If equation 1 is added to equation 2, which of these are changed? So let's add this equation 1 to equation 2. So then we have, so first equation will be the same. The second equation will be a bit different because we will have 2x plus 3y and plus 0z, and then we add 4 to 9, so it is 13. And the third equation is 0x plus 0y plus 4z, and the result is 16. Okay, so in this case, row picture will be different. Okay, so let's me back to this task. So if equation 1 is added to equation 2, which of these are changed? The planes in the row picture. Okay, so one of them will be changed, the second one. The vectors in the column picture, yeah, they will change because you can see that we have different coefficients now. So actually, the first row picture in the left side, in the left, will be changed, and this vector at the right also will be changed. And how about the solution? Of course, the solution will be the same. Okay, so yeah, the next equation is equation number 5. Next task is task number 5.
I think the coefficient matrix will also be changed, I think, apart from the row picture and the column picture.
Yeah, can you say it again?
I think the coefficient matrix will also change,
Yes,
like apart
sure.
from the row and the column picture.
Yeah, coefficient matrix will also change. So yes, yeah, we discuss still this task number 4. So the only thing that will remain the same will be solution only. Okay. And in this column picture, yeah, there's first vector on the left and the vector on the right will change, but coefficients, the coefficients of this linear combination, they won't change because we have still the same. Yeah, we have still the same solution to the system of equations. So yeah. So you can, if you want, you can try to solve this. If you would like to solve this system of equations, so this modified, you will try to do reverse operations. So instead of addition, the first equation to the second one, you will just do the reverse operation. So you would subtract the first equation from the second one, and these types of operations, these operations, they don't change the solution to the system of equations, to systems of equations. Okay, and yes, and now we have this task number 5. The first of these equations plus the second equals the third. So let me write this new system. So it is x plus y plus z is 2. X plus 2y plus z is 3. And 2x plus 3y plus 2z is 5. Okay, so we can see that if we add these coefficients in these first two equations, then we will obtain the third one. Okay, so x plus x is 2x, y plus 2y is 3y, z plus z is 2z, and 2 plus 3 is 5. Okay, and so we have this, now we have something to fill. So the third plane contains the line, that line. The first two planes meet along a line, and the third plane contains that line because x, y, z satisfy the first two equations. Then they also, okay, so what we need to write there, do you have any suggestions? So the first two planes meet along a line, okay, and the third plane contains that line because x, y, z satisfy two equations. They also satisfy, and we can say that they also satisfy the third equation, okay? We can check it by putting z equal to 0. Okay. Yes, it's true. I'm waiting because Sophia is typing. No, I just turned it off because I wanted to see this chat, and yeah, I will. Yes, yes. Yes, so the equations have infinitely many solutions in the whole line L. Find 3 solutions on L. Yes, and that's what Ritam showed. Yes, and so you can easily find many solutions of this line, which is intersection of the first two equations, but it's also in the plane described by or represented by the third equation. Okay, and yeah, can you, I will check if you can, yeah, you should see this screen sharing now. And then we have this exercise 6. Move the third plane from the previous problem to a parallel plane. 2x plus 3y plus 2z is equal to 9. Now the three equations have no solution. Why not? The first two planes meet along line, but the third plane doesn't. Okay, and doesn't contain this line. Okay, yeah, because we just moved it away by changing this number at the right side. Okay, so I think that we can start with this exercise 7, where we have to draw 3 lines. So in this case, you can please notice that we have a rectangular system of equations. So we have just 2 variables, but three equations. So the first equation is x plus 2y is 2. X minus y is also 2, and y is equal to 1. And now we can, as we just 2 variables, then we can draw illustrate these equations as lines. So the first equation, yeah, it intercepts x-axis in 2. When x is 0, then y should be 1. So that's the first line that corresponds to the first equation. The second equation, if y is 0, then x is 2. When x is 0, then y is minus 2. Yeah, is minus 2. So this is the second line, and the third line is y is equal to 1. So it will be a horizontal line. Yeah, so all those pairs of this line have common points, but there's no point that that belongs to all 3 lines. Okay, so in this case we don't have any solutions. We can also try to draw this column picture. So in this case we have this different dimensionalities of these spaces. So because for a row picture we can draw it in a plane, but for column picture we need 3-dimensional space. Yes, so the first vector has components 1, 1, 0 multiplied by x. Then we have plus, and we have 2 minus 1, 1 multiplied by y, and 2, 2, 1. Okay, so now we have, it will be difficult to as always, to draw three-dimensional pictures, but so yes, the first vector has these components 1, 1, 0. So this is E1, E2, and E3. And yes, so 1, 1, 0 should be somewhere here. Then we have 2, minus 1, 1. So the first component is 2. The second component is minus 1. And the third component is 1. Okay. So it should be somewhere here. Okay, so all linear combinations of these two vectors, they cover a plane in this three-dimensional space. Okay, and this third vector, 2, 2, 1, it is outside this. It's outside this plane. Okay, so it is in this three-dimensional space, but outside this plane. So this is the case when we don't have solution. So it means that there is no linear combination of these two vectors that will result in the third one. And we know that when we have two three-dimensional vectors, their linear combinations, the set of all their linear combination is can be illustrated as a plane in three-dimensional space. So this is how we can see it for this kind of equations. And is it possible to solve this system of equations? What will happen if in every equation will be 0 at the right side? So if there will be 0 at the right side, in the column picture, it will be easy to solve them because it is, yeah, so we know that that we can obtain this right vector by substituting 0 and 0 to x and y. And what will happen in this row picture if at the right hand side there will be zeros, then all these lines will be moved in such a way that they intercept origin of this coordinate system. So yeah, this line has should be 45 degrees and the last one. So all three lines will meet in the origin of this coordinate system. So this is what will happen if we change these right sides to zeros. Okay, so in this case, this system of linear equation is solvable. Okay, so we have about 30 minutes, 25 minutes. So now we can try with this method of Gauss elimination to find the solutions to systems of linear equations. So probably you know this method, but I will try to explain it anyway. So let's start with this system of equations from task number 8. So we have these three equations: 2u plus v plus w is 5, 4u minus 6v is minus 2, and minus 2u plus 7v plus 2w is 9. So we start with the first term in the first equation, and we call it pivot, and we want to subtract this first equation from the second and from the third equations in such a way to remove these first terms in each of these two equations. So we want to remove 4u, and we want also to remove minus 2u. And then we also try to remove this 7v. So I will start with this first pivot. So 2u. So this first equation will remain the same. And now I want to get rid of this 4u, so I need to subtract this first equation multiplied by 2 from the second equation. So 4 minus 2 times 2 is 0. Then we have minus 6 minus 2 times v, so it will be minus 8v. And then I subtract minus 2w from 0, so finally minus negative 2 minus 2 times 5 is minus 12. Yeah, so one step is done, and now we can also get rid of this element minus 2u, so I can just add this first equation to the third one. So 2u minus 2u is 0, v plus 7v is 8v, w plus 2w is 3w, and 5 plus 9 is 14. Okay. And this is what we had to do when the pivot was in the upper left corner. And then the next pivot will be the next one on this main diagonal. So we call these elements that they are in the diagonal. So the next pivot will be this one. And we need to get rid of everything below this pivot. So we will also modify this first equation. So I will rewrite these first two equations. Minus 12. Okay, so minus 8 plus 8 is 0, minus 2. So now I just need to add this second equation to the third one. So minus 8 plus 8 is 0, minus 2 plus 3 is 1, and 14 minus 12 is 2. Okay, so now we have first stage of this method is accomplished because this system of equations is triangular now. So in the first equation we have just one unknown, so yeah, it is actually known because we know that W is 2. Then I can substitute this 2 to this second equation and find out what V is. And then if I know V and W, I can substitute them to the first equation and find U. So this is called back substitution. So we start with this W is equal to 2. When I substitute 2 here, then I will have -4. So if I add 4 to both sides, it will then it will mean that -8 is -8V is -8. So it means that V is equal to 1. And if I substitute 1 and 2 to the first equation, I will have 2U plus 3 is 5. So I can subtract 3 from both sides, and I will obtain 2U is equal to 2. So it means that U is also 1. And you can easily check if this solution is correct. So 2 plus 1 is 3, plus 2 is 5. Then we have 4, minus 6 is -2, and -2 plus 5 plus 7 is 5, plus 2 times 2 is 9. Okay, so that's the one way to solve it, by starting from this triangular system of equations. So we can use this back substitution. But we can also instead of this back substitution, we can continue elimination. So now we can use this pivot and get rid of everything above this pivot. And then we use this element as a pivot, and also we need to remove these elements above it. And finally, we will obtain a diagonal system of equations. So we have this third equation, and now I want to remove this -2. So I need to multiply this third equation by appropriate number in order to remove this second term here. So I need to multiply the third equation by 2 and add it to the second one. So I will obtain -8V plus 0, and then I multiply 2 by 2, which is 4, -12 is also -8. Okay, and then I still use the same pivot because I need to remove everything above it. So I need to remove also this W. So in order to do it, I need to subtract this third equation from the first one. So I will obtain 2U plus V, and I subtract the V from W from W, which is 0, and 2 from 5, so it is 3. Yeah, and finally, I need to, I can use this term as a pivot and remove this term above it. So FW minus 8V is -8, and I can multiply this second equation by or divide the second equation by 8 and add it to the first one. So it will be 2U plus 0 plus 0, and then Yeah, so that's the second stage. So it was elimination. It was upper elimination, and finally I can divide each of equations in order to find out these solutions. So the first equation can be multiplied by 1, can be divided by 2, so u is 1. Then the second can be divided by -8, so v is also 1, and w is 2. So yeah, these are two types of continuing from this. So this this elimination method, the first stage is to transform this system of equations into upper triangular system of equation, and then we can continue. We have two options to continue by back substitution, or we can also continue with elimination. Of course, I know that you can try to change order to simplify this process, but anyway, this in most of time this algorithm will work and will get you to solutions. So it can be easily you can easily write code and try to solve these kind of linear systems by using a computer. Okay. Yes. So I will check if you can see any questions. So yeah, now we have the rest of these solution, the systems of equations. These tasks are to find the solutions. This just to exercise this this method of Gauss elimination, and so you can try to do it yourself. I think that in the case of this task number 9 or 10, it will be difficult to the numbers are not easy there, so you can just skip this. If you will find that in 9 or 10 there will be quite difficult fractions, and it will be difficult it will be tedious to finish it. So I think that I can and now I will still be available here, but I would like you to try to use this Gauss elimination method to finish these exercises. And if you will have any questions, please write them on the chat. So yeah, good luck, and I'll be here till 15. Okay, so it's a good question. What will be condition for no solution? So there you can have a situation when this number that you in this place that you want to use as a pivot will be 0, and then what you can try to do is to exchange rows, as we know that this kind of operation it doesn't change the solutions. So if there's no way to exchange rows and have so we need to have non-zero value at the pivot position, and there is no way of doing it by exchanging rows. Then it means that there is no solution. Okay, and yes, actually, this will also occur when there will be infinite number of solutions. So in this case, one of the equations would be would have all coefficients equal to 0, and it means that one of these equations is dependent of the other two, and it means that there are infinite that there is infinite number of solutions. So yeah, maybe I can also try with this exercise number 12, where there is need to change rows to get the solution. Okay, so well, okay, so I will try this exercise number 12. Okay, I think I need to wait for screen sharing. If number of variables is equal to number of equations, okay, I'm trying to do this screen sharing. Okay, so now I think that will be good to try this exercise number 12. We have this u plus v. Oh, okay. Plus w is equal to -2. 3u plus v minus w is 6, and u minus v plus w is minus 1. So first we have this pivot, and the first equation can be rewritten, and then we need to multiply. In order to remove 3u, we need to multiply this first equation by 3 and subtract it from the second one. So we will have 0u, then we have 3v minus 3v. It will be also 0. And minus w minus 3 times w, it is minus 4 times w, and 6. Okay, so minus 6 minus 3 times minus 2. Oh, minus 3 times minus 2, it will be 12. Okay, so now in this pivot position we have 0 because there is 0v here, but we can continue with this first pivot and we will see what will happen below. So in order to remove u from the third equation, we need to subtract the first equation from the third one. So u minus u is 0, v minus v is minus 2v, and w minus w is 0. And then we have minus 1 minus negative 2 is 1. Okay, so now we can't continue with this pivot because it is not possible to eliminate anything. But yes, actually you can easily read the solution because these two equations have only one unknown. But if it's not the case, then you can just interchange these rows and continue with it. So now you can easily find out that v is minus 1 over 2, and w is negative 3, and then you can substitute these two values into the first equation and find the solution to u, to variable u. Of course, we will have many more examples of this kind of exercises, also for rectangular systems of equations. So I think that you get better with this.
So, can you use the Gaussian method of elimination, but with like matrices instead of writing 1x plus 2y plus 3,
Yeah.
1,
Yeah,
2, 3.
sure. We will do it on the next classes. Okay, so
Yeah, sure.
because I guess you are much more familiar with this kind of notation using this. Using all these multiplications, and yeah, the next time we will start with matrices, and we will also do exercises with operations of these matrices.
Okay, thank you.
You're welcome. Okay, so I think that we can finish now. So Thank you for your attention, and see you next Wednesday.
Bye.
Goodbye.